Welcome to class number 9, session number 2. This session will focus on the synthesis and production approaches of polymeric nanostructures. In the following slides, we will see different methods for creating the conductive polymer nanostructure, and we will examine ways to control the properties of these products. Template methods are emerging for a sort of facile, efficient, and highly controllable synthesis of conducting polymer nanostructures. In the following slides, we will present and discuss template synthesis routes for conducting polymer nanostructures. The template synthesis route of conducting polymers include, as a matter of fact, from soft template and hard template methods. The former lies on molecular self-assembly to form nanostructures, while the latter replicates existing nanostructure by physical or chemical interactions. The scheme presented on the right side of the screen illustrates the template synthesis of conducting polymer nanostructure throughout the soft template methods and, secondly, throughout the hard template method. The soft template method includes, among the rest, microemulsion and reversed microemulsion synthesis, and also it includes non-template or so-called self-template synthesis, in which monomer or oligomer forms structural micelles by themselves. The hard template method includes, among the rest, physical templating against existing nanostructure of particles, structural replicates against nanochannels, reactive template method, which clone nanostructures by the chemical reaction between template and monomers. We will discuss part of these approaches in the upcoming slides one by one. The hard template synthesis employs a physical template as a scaffold for the growth of conducting polymers. The hard template scaffold includes colloidal particles and some templates with a nano-sized channel, such as anodized alumina oxide, which is abbreviated as AAO, and mesoporous silica carbon templates. For the synthesis with micro nanoparticles or nanoparticle templates, the target material is precipitated or polymerized on the surface of the template, which results in a core shell structure. After removal of the template, hollow nanocapsule or nanotubes can be obtained. The most commonly used hard templates include monodispersed inorganic oxide nanoparticles and polymer microspheres. Basically, a template with a nano-sized channel can be used to produce conducting polymer nanowires or tubes with restricted deposition growth effect. This kind of templating method is characterized by high controllability to produce nanowire or tube nanostructures, and most importantly, the related arrays. In this approach, the conducting polymer nanostructures can be formed by filling the templates throughout physical or electrochemical deposition of the targeted material. The commonly used and commercially available templates of this sort are anodized alumina oxide membrane, radiation track etched polycarbonate membranes, zeolites, and mesoporous carbon. One of the most attractive advantages of this route is that the ordered array of the conducting polymer nanotubes can be produced using the alumina oxide template. Most materials prepared by this approach showed so far good low-field conductivity, which demonstrate that conjugated polymers can be encapsulated in nanometer channels and still support the mobile of charge carriers. An example of the hard templating of polymeric nanostructure is presented on the screen. The same image stands for the developed template by self-removing process to produce a polyaniline hollow structure with octahedral cuprous oxide as template as shown in the figure, which was spontaneously removed by reaction with an oxidative initiator, ammonium peroxydisulfate. The advantage of the hard template method can be summarized as follows. The diameter of the nanostructure is controlled by the size of the pores or channels in the membrane, whereas the length and the thickness of the nanostructure is usually adjusted by changing the polymerization time. For this reason, the hard template method is the most commonly used and the most efficient approach for preparing well-controlled and highly oriented nanostructures. And in this case, the diameter of the conducting polymer in the format of nanowire can achieve as small as 3 nanometers. On the other hand, disadvantages of the hard template method are quite obvious and are summarized as follows. The first disadvantage is that using a membrane as a template requires post-processing to remove the template. This action complicates the preparation process, and post-process can often destroy and disorder the formed nanostructure. The second disadvantage is that the quantity of the nanostructures produced by this method is limited by the size of the template membrane, which thereby limits its applications in large-scale nanostructure production. The soft template synthesis, also named self-assembly method, employs micelles formed by surfactants to confine the polymerization of conducting polymers into low-dimensional nanomaterials. Typical synthesis of this sort includes microemulsion polymerization and reversed microemulsion polymerization, in which surfactants are involved, and the non-template or self-template synthesis, in which the monomer or its salts form micelles by itself. This method is a relatively simple, cheap, and powerful approach for fabricating conducting polymer nanostructures throughout self-assembly process, which is based on selective control of non-covalent interactions, such as hydrogen bonds, van der Waals forces, pi-pi stacking interaction, metal coordination, and dispersive forces as the driving forces of the self-assembly. The scheme presented on the screen shows the representative mechanisms of the soft template synthesis of different conducting polymer nanostructures. In the first mechanism, micelles act as a soft template in the formation of the nanotubes. Micelles are formed by the self-assembly of dopant, and the polymerization are carried out on the surface of the micelles. In the second mechanism, nanowires formed by the protection of dopants. The polymerization in this case are carried out inside the micelles themselves. In the third mechanism, monomer droplets act as soft templates in the formation of the microspheres, and in the fourth mechanism, polymerization on the substrate producing aligned nanowire arrays are illustrated. In this case, nanowires are protected by the dopants, and polymerization preferred to carry out on the tips of the nanowires. The soft template method owns the advantages of low cost and large yield, which is suitable for the production in large quantities in one pot. Meanwhile, some routes that involve multi-phase solution, such as the microemulsion, reverse microemulsion, and self-template method, have great potential for synthesizing in organic conductive polymer composite nanostructures by the interfacial reactions. The shortage of the soft template method in energy storage devices rises from the discontinuous morphology of particles in electrode, which actually increases the electronic impedance in certain extent. Reversed microemulsion, namely water-in-oil polymerization, generates conducting polymer nanostructures such as monodispersed nanoparticles and nanotube or rods, with morphology controlled by introducing the interaction between the ions and the surfactant. Researchers have fabricated polypyrrole nanotubes throughout chemical oxidation polymerization in reverse emulsion in a nonpolar solvent. Reverse cylindrical micelles are formed and a pyrrole monomers introduced into the reverse cylindrical micelle phase are then rapidly polymerized along the surface of the reverse cylindrical micelles. This action actually results in the formation of polypyrrole nanotubes as illustrated on the screen. In the self-template synthesis described on the current screen, the monomer of conducting polymers or its salt form micelles by themselves, which act as templates for the formation of nanostructures. So far, researchers conducting a thorough research in this field regarding the universality, controllability, and self-assembly mechanism by changing the polymeric chain length, polymerization method, dopant structure, and reaction conditions. The researchers have synthesized a variety of micro or nanotubes, nanofibers, and nanotube junctions with this approach. The figure seen on the screen shows conductive polymer nanotube junctions and their aggregated dendrites fabricated using non-templating or the self-assembly method. In panels A to C, one can see transmission electron microscopy images of polyaniline nanotube. In panel D, one can see scanning electron microscopy image of polyaniline nanotube junctions, and in panel E on the screen, one can see the SEM image of polypyrrole dendrites. A promising approach for the production of the nanostructured polymeric materials relies on the electrospinning. We have explained about the operation mode of this approach in class number 8. Nevertheless, I will repeat quite briefly and explain that electrospinning is an effective approach to fabricate long polymer fibers with diameter from micrometers down to hundreds of nanometers or even few nanometers by using strong electrostatic forces. As shown in the figure presented on the screen, in the usual electrospinning process, polymer solution is extruded from an orifice to form a small droplet in the presence of electric field, and then the charged solution jets are extruded from the cone. In general, the fluid extension occurs first in uniform and then straight flow lines undergo vigorous whipping and or splitting motion due to the fluid instability and electrically driven bending instability. One of the most important advantages of the electrospinning technique is that it's relatively easy and not expensive to produce large numbers of different kinds of nanofibers. Other advantages of the electrospinning technique are the ability to control the fiber diameter, the high surface-to-volume ratio, high aspect ratio, and pore size as non-woven fabrics. Compared with the other synthetic approaches, the electrospinning process seems to be the only method that can mass-produce continuous long nanofibers. In the current screen, you can find a video that shows polymeric fiber that is generated by the electrospinning approach. On the left side of the screen, you can see the end of the needle, from which long nanofibers are extruded, as could be illustrated and seen on the right side on the screen. We come now to the end of class number 9, session number 2. Thank you.